Hello everyone, my name is Gijs Molenaar, and I'm going to talk about our transients detection pipeline. I'm a scientific software engineer working for the University of Amsterdam, and since a month I'm also an unpaid remote PhD student in South Africa. I'm not sure yet how that is going to work, but I'm going there next month for a couple of months to work on another telescope or software for another telescope. I'm actually not an astronomer. I have a background in artificial intelligence. I have a master's degree in artificial intelligence and more specialized in computer vision and video processing. So in Amsterdam, I'm working for the Anton Pannekoek Institute, which is the astronomy department of the University of Amsterdam. And in South Africa, I work for the Square Kilometer Array project, which is the organization that builds the South African part of the Square Kilometer Array, which is a huge telescope which will be finished in 10 years. So what I do is that I build software for processing telescope output that is used by scientists to do science. So I'm not doing science myself, or at least not yet. In South Africa, so that's what I do in Amsterdam, and in South Africa, what I do is, I'll do some science, and that's working on design patterns and software techniques for open and reproducible data reduction. So that's the title of my thesis. And I'm trying to improve the software landscape in radio astronomy. And in my opinion, it's quite poor. So, and I hope that maybe I can also help in other fields and not only radio astronomy. But today I will talk about TRAP, the transients detection pipeline. And I'm specifically focusing on how it is made or how we make it. The transients detection pipeline is a work in progress, so it's actually not operational yet, or not fully, but it's partly being used by scientists, but it will take a while before actually real transients are being detected. So I don't have amazing graphs and interesting figures, but that's why I also want to focus on how we actually make it and what tools we use for that. So this is LOFAR. It stands for Low Frequency Array. This is the core station of the telescope. It's in the Netherlands. We call it the SuperTurp. It's totally different than from a traditional telescope where you have a mirror or a lens. And this is based on antennas. So you also have radio telescopes that are based on dishes, but this is quite new, that it's using antennas and a lot of them. So this field consists of, I don't know the exact number, but a couple of hundred antennas, just wires, antennas. And, but there, so this is the SuperTurp. This is the central part, but there are also many substations. So they are scattered around Europe. There's some in the Netherlands itself, so the substations are the same as the SuperTurp but smaller. And there are some in Germany, there's also in Poland and in Finland, I believe. So, and these signals can be combined to create images of the sky. And the wider the distance between the substations, the high resolution images you can create. LOFAR is seen as a sort of precursor for SKA, which will be this huge telescope that I'm talking about. It's partly already existing. This is a picture of KAT-7, which is, it stands for Kourou Array Telescope, I believe. And then it consists of 7 dishes. And this is now being extended to 64 dishes. The name is Meerkat here, which is, Meerkat is more cat. It's an Afrikaans joke. And this is an artist's impression on how it will look in 10 years. The idea is that thousands of dishes will be built in the desert They're building a factory there for building dishes. So it's a huge project. It's a multi-tens of billions euro project or rents. Data rates will be enormous. The data rates coming out of this telescope will be more than is being transferred on the internet as a whole at this moment. So completely new techniques need to be invented to process this huge amount of data. So I'm not going to dive too much in how you do radio astronomy with interferometry, but just a really quick introduction that it's based on the principle that you have multiple receivers and you know exactly what is the difference between the receivers, and you have a object in the sky emitting electromagnetic waves. A wave front comes in and there is a phase difference between the receivers, and if you compensate for this phase difference, then you can say something about the orientation of the wavefront. So if you have more receivers, you can do better triangulation, and if you have even more, you can do you can create images with that by doing inverse two-dimensional Fourier transformations. So how does this look like? These are images created with LOFAR with I think about 40 hours integration time. Integration time is similar to exposure time in optical photography. This is a complex shape, but that's not the point of interest. I think this is the point of interest, which is it's supposed to be a famous microquasar. I don't know it, but in astronomy everybody knows it, it seems. And this is a new image because this object has never been observed at these low frequencies. So LOFAR operates at really low frequencies, and images, it can create images that have not been created before. So here's another interesting image. That this is a composition of two images. I was a bit disappointed when I joined astronomy that when you look at these pictures, that actually many of them are artist impressions. So all the fancy colors, they are all artificial. So the idea is that you take images of an object in various frequencies and you combine them and you color code the frequencies. So this is the same here. I think the blue is LOFAR and the red is an X-ray telescope. And these are jets coming out of a binary black hole system or something. I don't know. So a transient. I'm not a native English speaker, so I did not know what was a transient. I had to look it up in a dictionary, and it is a lasting only for a short time impermanent. So what we're looking at, we're building a pipeline that detects things that change in the sky. So, and we do that by having a huge data reduction triangle. So we have the telescope here. It gives raw data at a rate of about 50 gigabits per second. And it goes into the pipeline. We have multiple steps in the pipeline. And eventually, the resulting data is presented in a web interface. And the scientists can do science with that. Also, so I'm focusing on this part because it's pure Python. So everything after about half of the pipeline, after the moment that we have images, it's all Python. So there's a couple of weeks ago we removed the last piece of C code, and everything is pure Python. So this is hardcore low-level stuff. I'm not going to focus on that, but this is GPUs, FPGAs, and stuff like that does the hardcore computational stuff, and that delivers us the images, and we take these images as input for the transient detection pipeline. So we don't only show this in a web interface. Idea is also eventually that when we detect the transients, we will sort of emit a alarm into a distributed network of astronomers, which can then focus their telescope on this specific object. So it's the idea is that for the transients detection pipeline, it will function as a alarm system for astronomers also. The good thing with a radio telescope is that multiple users can use it at the same time. So a traditional telescope, you aim at something, and then you cannot aim it at something else at the same time. So the good thing with a radio telescope is that you can take the same data coming from the telescope, and you can just interpret it in a different way, and you can aim it at something else. So what we do, we have a sort of sub-project within LOFAR where we take the data raw and we put it in our own correlators and imagers, and what we do is we create a wild field of view. So another astronomer can focus on a really interesting pulsar or something, but we want to have a wild field of view. And so we can detect as much transients as possible. The consequence of that is that the images are a bit lower quality, also because we can only use the SuperTurb because the data rates are so incredibly high. We do this real time, so the idea is that we create one image per second per frequency band. And we have 10 sub-bands. We divide the spectrum up in 10 sub-bands. So we have 10 images per second, and they look like this. Quality will increase, but this is what we work with now. So we label these sources. We call this source extraction, and these numbers are then used in the pipeline for later usage. So source extraction works in the way that you can see the image as a three-dimensional landscape, and you have spikes in it, and you want to fit a two-dimensional Gaussian on these spikes. So when we have fitted this Gaussian, we take the position, the frequency, the time and the shape of the Gaussian, and also the intensity of the object, the flux. So, and this is all stored in a database. So we have one big table with all these measurements, and this is the base of our processing pipeline. So the next step is that we do source association in time and in frequency. So we just have a matching algorithm that checks in the database if an image in the next time step is reasonably near, and if it is, then they are sort of linked. This will result in light curves. So this is a light curve. It's not really interesting. It's just quite noisy, but it's a light curve. So a bit more about the data rates. So we call the images from the set of images from the various subbands, we call them data cubes. And there are about 50 sources at the moment we can detect in these images. So these are 500 source measurements per second are going into the database. We're looking into if we can improve the imaging pipeline, and we can increase the data rate to about 10 images per second, or 10 steps per second. So this would imply that we get about 5,000 sources per second. Or database inserts. This number will grow as telescopes get more sensitive and algorithms improve for calibrating the telescope, which is a science on itself. So it's a lot of data, and the idea is that we optimize our problem by moving our calculations to the data, just like similar to how MapReduce works. So what we do is we build gigantic SQL queries that we transfer to the database, and there they are executed, and the resulting data is then written back to the database. So this minimizes communication, and communication is really expensive in computer time. So we use SQL, and we use SQL because our data is highly structured. We know the schema before, and also the data is relational. So, and another big advantage in this field is that the data is also highly chartable, because the sky is dividable in parts, in shards, and these are independent of each other. So, but the query, you cannot read it, but the idea is that we have huge SQL queries, and these are quite hard to work with. They are hard to read, hard to reason about, and hard to take apart, and thus hard to test, and also hard to reuse. So you get a lot of code duplication. So it makes it all quite hard to maintain. Server-side functions can be an option, but that implies moving your logic into your database, and also function syntax differs per database engine. So we're currently looking into SQL Alchemy to assist us in this problem, and there are some prototypes based on where we split up the function and we have reusable code. So, yeah. So we have multiple database backends. Traditionally, when I joined the project, we only supported MonetDB. MonetDB is a not so known database engine. It's developed at CWI. CWI, it's also where Python comes from. And they are developing a column store database engine that is really fast on big data sets. So, but the problem is that MonetDB is not that well known, so not many tools support it, like SQL Alchemy or Django. And so we were a bit stuck in that situation. We could not switch databases to do benchmark comparisons and such. So after some effort, we now also support Postgres, so we can do comparison and also plug in our pipeline in other tools that support Postgres. Water. So for that, we needed to create SQL Alchemy dialects for MonetDB and also a Django backend for MonetDB. So I've made these. I've never received a bug report, so I think nobody's using them. But but please feel free to use it. So yeah, it works for us, but probably there are many bugs. So if you have time left, then. So about parallelization, in the beginning we were using IPython for parallelization. We thought this is going to be such a complex problem. We need a cluster of machines to do all this work, and we started with IPython. That was ditched for a reason I don't know, but IPython back then was not good. I don't know why. We switched to a homebrew SSH-based solution that was ditched because it was no good. Then we switched to Celery, where we made a sort of homemade MapReduce, and that was ditched. That's my fault. And eventually we switched back to multiprocessing. So we have a single system now. Now, 2 or 3 years later in time, machines are fast enough, we discovered, to just do it all in one machine, one big beefy machine with 64 cores. So it's a typical example of premature optimization, and it's sometimes you just see that too late. And but maybe we will switch back to IPython again now with the IP engine and stuff like that. Visualization. So we made a visualization tool. It's a web interface. We call it Banana. It's based on Django. It's a high chart for creating the charts. Bootstrap for nice formatting of all the tables and all the menus and stuff like that. We use a little bit of AstroPy and ApplePy. The reason why we don't use it that much is that in radio astronomy we already have a library called CasaCore and a Python wrappers that does a lot of the position conversion and stuff like that. It's not well maintained, or it is maintained, but there are not many people using it. So maybe it's idea to start using AstroPy a bit more in the future, but for now we use CasaCore a lot. This is a screenshot of the web interface. So this is what the scientists use. This is the original image with labeled objects, and they can get details of every object and click through and find the light curve. They can find all kind of properties of the object. Another screenshot, this is the light curve view. So we don't have a lot of data yet, but this is the light curve of a object. It's connected to other services, web services that give information on a specific position. So if something interesting is happening, then people can click through. And so sure, you can manually look it up, but it's much easier to have buttons that do that for you. A little bit about our development process. So we use GitHub. We have, just as in the kindergarten, we have a 4i policy. We do pull requests, so nobody can directly commit unless necessary or trivial. So every change we do is authorized by somebody else in the team. Everything needs to be documented for the end user, but also for the internal developers. Nothing is accepted now anymore if it's not unit tested. So slowly the coverage of the unit tests are growing, and it's at 77% now. We also do automated testing using Jenkins and Travis. So Travis is nice, it's free, and if you have a GitHub repository, you have unit tests, I advise you to run Travis. and but we have our repository is private yet. So still, it will be public soon. But so we use Jenkins. Also, Jenkins offers a lot of plugins for doing all kind of measurements or extra visualizations of your test results. So it's yeah. Also, we have a performance plugin installed for Jenkins. This measures the timing of all the unit tests in our tests run, and if there is a big decrease in a time, if there is a regression problem, then an alarm goes off and we are notified. So if you change an algorithm that gets much slower, we will get noticed. For central communication, we use HipChat. We have users and developers in various countries. Australia, England, UK, Netherlands. So everything that's happening, every commit, every test result, every discussion is central in HipChat. And we have various channels per sub-project. So also when there's a problem, an astronomer can ask questions there and get tech support. So we integrated the test results with the pull request. So if the test suite runs completely successfully on a pull request, then the GitHub pages are updated. So yeah, we have extended documentation. This is for the end user, but also for the developers himself. It contains the documentation of the database scheme or some technical parts or the mathematical formulas behind algorithms, but also contains everything for getting up and running quickly. So for deployment, we will have just a pip installable package, but you need to do a bit more to get the library working. You need to install a database, install the schema, set up a web server and connect it to Banana. So it's quite hard for an end user, a scientist, to do this on their own. So what we have made is a virtual machine-based solution that does this for you. So it's based on Vagrant. Vagrant is a thin layer around VirtualBox, and it's a scripted way of creating virtual machine images. And an end user can now just install Vagrant, check out a GitHub repository, run Vagrant up, and she or he has the pipeline running. There's a small overhead in virtualization. So we're looking now into Docker, which is a more efficient way of doing virtualization or containing your application. But for now, Vagrant is the preferred solution because it's more stable. So the status is that 2.0 is almost ready of the pipeline. If this is ready, the paper will first be released, because when scientists use it, they need to cite the paper, and so there's a decision being made. But if the paper is published, everything will be open sourced and BSD licensed. Banana is already open source, but it's useless without the trap because you have nothing to populate the database. Future plans. Well, looking around, I thought it's a good idea to start switching some of the functionality of our Banana to an IPython notebook, because it's much easier for customizing queries and doing more advanced stuff if a scientist wants to. So if he doesn't, then he can just use an IPython notebook, but it's much easier to change variables than to have a static website where everything needs to be done by software engineers. So in the long run, I think also it's a good idea to implement a public REST interface where other people can query the database, other astronomers around the world, and compare measurements, or just like how we use other services. That's about it. Yeah, are there any questions? Thank you. Yeah, the mic is coming.
Hi, thank you. How do you do when you detect sources? You said that you have to point to to adjust the calculation to point to a certain direction. Does it mean that if you have an image of certain field of view, you have to use, I don't know, 2,000 times 2,000 different setups to create an image, and then you look for sources, or there is a trick to overcome this quite CPU expensive.
Sorry,
stuff.
I don't get the question. What?
If you create an image
Yeah.
with sources in there, at the beginning you said that to point a certain direction, you have to adjust the like a processing algorithm itself.
Right. Yeah.
So,
That's the.
so how do you like create different pixels of the image? Does it mean that they are like one pointing, which like goes bad in precision once you go off axis, or does it mean that you run the analysis or the convolution of the signal, let's say, a million times?
It's I don't know. So this is not the part where I've been working on. In theory, I know a bit about that, but it's some parameters you change in the algorithms you have with the reverse two-dimensional frequency Fourier transformation. Yeah, I don't know. Sorry. Yes, here. Oh, sorry. Yeah, then.
Thank you. You mentioned that you switched from Celery to multiprocessing approach. What was the reason? Was it because you wanted to avoid having workers doing scheduled tasks and you want to have more parallelized, more performance on multiprocessing, I mean using several cores in your machine? What was the reason for switching from one approach to the other one?
The parallelization method.
Exactly.
So we used Celery as a sort of MapReduce, where we had a cluster of computers and we sent some input to some functions which could be executed independently, and then gathered the results again. So first problem is data locality. You need to move your data there, and you can solve that with a distributed file system also, but you add a lot of complexity to your system. So in the end, people were using it. It was fragile. It broke down easily. And we eventually decided that it's much simpler just to have a multiprocessing solution for our problem. So some of the problems here are really easy to parallelize. For example, the image analysis. Like if you have 10 images and you do source extraction on them, these are completely independent of each other. So you can fan out 10 processes that do source extraction and gather the results, and then do database interaction again, which is not parallelizable.
Okay, yeah, I was thinking of the fact that if one day you're exposing your API, your REST API to the public, then having just one computer saving the needs, it's going to be probably overloaded very
Yeah, but
rapidly.
then the data is already processed, right? So we have a database that is populated with these results, and then people can query this. So it's just an archive of data. So there's no
processing.
No.
Okay.
No.
All right.
That's done continuously, and people can query the results. So.
Great. Thanks.
Any other question? I see the one there.
Do you actually plan to open up the data cubes so that scientists can then make their own queries in the future? And if so, how? That seems like an incredibly complicated problem. How would you be able to do that? Do you have any ideas?
Well, I'm not the guy to answer that. I don't know. There's also kind of legal problems with that, right? People build this telescope, and some scientists then can use it, and others not. I think it should be open. Another problem is that the data rates are immense. Now we store these images, but in the long term we cannot store these images because it will quickly become terabytes of data. So it depends a bit. Maybe what you can do is, for example, if something interesting happens, then you start a snapshot and you record that. So, but I don't know. Yeah. Does that answer your question, sort of? Yeah.
All right. Didn't see any more questions, so thank you, guys.